Hello, everybody. So, in this one, our final lesson on Chapter 8, we are going to be looking at improper integrals. So, what that means, really, let's go back to our base definition of integrals. If I had the integral from a to b of f of x dx, then this would work out to the antiderivative of b minus the antiderivative of a. Two key things had to be true. One thing is that I needed to be existent from A to B. Also, I must be continuous on that interval as well. So these two things have to be met before I can just do direct substitution into these things. So one thing to note here with our first one is that I have an infinity as my upper bound. So what that means for us is I have something that is not inclusive there, since infinity would include a parentheses. And I can't necessarily say that it goes to some defined value. That's going away from all numbers that I even know. So this doesn't really work for us, but we're going to try to use something such that, yes, I know I don't necessarily get to this value, but I would like to say that I'm going to approach infinity. I'm going to go to infinity. And the thing that we use in calculus that allows us to do that is limits. So what we can do is say, hey, I'm gonna say the limit as b approaches infinity from 0 to b of 1 over x squared plus 1. And what that allows me to do is now I'm just putting in a b. A b is a defined thing. I can put that in. And then at the very end, I will evaluate my limit. Unless you take this initial step, if you start doing your integration, you're going to lose all points on the problem. So this very initial step, recognizing that that is improper, that is something that cannot be done with our base definition of integration, you need to write out this limit. So then I can do the limit as b approaches infinity. The antiderivative of 1 over x squared plus 1 is arctangent from 0 to b. And then I can throw in my b. Minus arctan of 0. So now you have to remember some unit circle facts and remember some inverse trig facts. Tangent has asymptotes at pi over 2 and negative pi over 2. So if I do arctan, right, this is just tangent. If I do arctan, right, for inverse functions, the x equals asymptotes will become y equals asymptotes. So I have asymptotes at positive pi over 2 and negative pi over 2. And arctangent will reflect over the line y equals x. And I get a graph something like that. So what that means for this part is now if I evaluate my limit, if I throw an infinity for that b, arctangent as it approaches infinity, going out this direction forever, will approach positive pi over 2. And arctangent of 0 is right there. That is also 0. So pi over 2 minus 0 is my answer. So just pi over 2. Right? They're going to be looking for every single step here. There's really not anything that you can skip. You need to have your initial step with the integration and the limits, recognizing that this is an improper integral. You need to have the antiderivative shown clearly. You need to have the substitution with the variables. You can't just evaluate that infinity and skip straight to there. You need to show this first because this is just kind of a function still. So until you do this step, you can't give us that answer. You could do, really the only thing that you could skip here is you could have done in your head that arctangent of 0 is 0, and then say that I'm going to evaluate the limit as b approaches infinity of arctangent of b. But other than that, everything needs to be there. Okay, so that is one type of improper integral, where I am approaching infinity. So let's take a look at our next one. I think this was just an example that I had you guys do in class. So let's just roll through it real quick. Again, I have an infinity. It is an upper bound. Normally, lower bounds will be a's, upper bounds will be b's. It really makes no difference what variable you do, but this is what's commonly used. The lower bound is a and the upper bound is b. So if you're looking at textbooks and things like that, that's probably what you will see. Okay, so infinity is my issue here. So I'm going to say that this is the limit as b approaches infinity of 1 to b, 1 over x dx. The antiderivative of that is natural log. From 1 to b, then let's throw in our b. So ln of b minus ln of 1, which is 0, so I didn't have to write that. And now natural log as I go out forever. Natural log looks like this. And as it goes out forever, it's going straight up. So that will go to infinity. So what that means for us is if this is going to infinity, this is a divergent integral. So it's diverging away from all numbers that I know. So my answer isn't really infinity, it is diverging away. So I would just write that this is divergent. On this last one, technically, what is happening is it's getting so close, right? This is going to infinity. The graph of 1 over x squared plus 1 looks like something like that. So I'm doing the area from 0 to infinity. And how can I really tell that that is pi over 2? And this is just because what we say it converges to pi over 2. It doesn't actually get exactly there, right? That's what kind of limits allow us to do, is say I'm not actually there, but I'm getting so close that it might as well be that number as well. So I'm converging to that number. So they may have it listed as converges to some number, or it diverges away from everything, or just they'll probably just put diverges. But all right, moving on. So now this one looks all nice and innocent, right? But let's think about the graph of 1 over root x. Really, truly, the x value I cannot have is 0, because if I put in 0, that would be 1 over 0, so I should have an asymptote there. And we do. It'll look something-ish like that. So I'm trying to calculate the area from 0 to 4. Well, here, my lower bound is my issue, and I only want to approach it from one side, because if I just put the limit as a approaches 0, that would imply that a is both approaching from the left and from the right. But here, because this is where my, you can't see that, this is where my area is, I want to just approach from the right-hand side. So I will add 0 from the positive side of my integral from a to 4 of dx. I'll write that off to the side. And let me do x to the negative 1/2 so I can see my power rule more clearly. And then I can do my antiderivative. So add 1 to the exponent, so x to the 1/2 times 2 from a to 4. I can throw in my 4, I can throw in my a, so limit as a approaches 0 from the right of 2 root 4 minus 2 root a. Right, and then as a is approaching 0 for that, this is going to be 0, so this whole part will be 0, so I will just have 2 times the square root of 4, which is 2 root 2, or sorry, not 2 root 2, 2 times 2, which is 4. All right, so I didn't have an infinity, but I did have kind of an infinite discontinuity that I needed to work around. Okay, part D here. So this one I have the infinity. There's no like denominator. Kind of technically there is, right, with the e to the x, but that's not going to be ever equal to 0. So I'm not going to worry about that. I'm not even going to rewrite it, because I'm thinking that I'm probably going to do integration by parts here. So I will want to rewrite this. And this is an easy one to do with the alternating signs for my uv, right? Remember that it is uv minus the integral of v du, where I pick a u and a dv to set that equal to. This is our integration by parts rule. But our tabular method allows us to kind of skip over that stuff. So 1 minus x is the part that's going to go eventually to 0. I'll need to do the antiderivative of e to the negative x, which is easy enough. And then alternate my signs. And then I will go over and down to come up with my antiderivative. So I just done gots. Limit as b approaches infinity. So 1 minus x times negative e to the negative x. I'm going to put that negative e to the negative x out front. Times 1 minus x. And then, let's see, I have positive e to the negative x, so plus e to the negative x from 1 to b. Okay, and when I evaluate this stuff, I'm going to think about these e to the negative x's as 1 over e to the x, just to make my life a little bit easier. So I'll write it out that way. So limit as b approaches infinity of, throw in my b first, so 1 minus b over, it's going to be negative e to the b, plus 1 over e to the b, and then minus, now I got to throw in the 1, so 1 minus 1 negative over e to the 1 plus e to the negative 1, which will be 1 over e. I don't know why I did it that way. Right. And now I can evaluate my limit. So I'm throwing in b is infinity, so this is 1 minus infinity over e to the infinity. If you think about this as L'Hopital's, right, because it'd be infinity over infinity. If you did the derivative, it'd be 1 over e to the infinity. So this part should go to 0. This will also go to 0. This is 0. 1 minus 1 is 0 over e. So really all I'm left with is 1 over e, but it's negative since I need to distribute that. So this comes out as negative 1 over e, and that is it. Alrighty. Ooh. So this one has 2 infinities. So what we can do, I was at an AP conference this past summer. This would have been 2021. But I asked one of the presenters, this was one of my big things, is when I talked to a student from an AP class in 2020, they asked, hey, can I do this? Right, because that would seem to make sense, right? Negative infinity to infinity. And I said, I don't know. I will ask. But for now, don't do that because that's not how we have taught you. So when I asked this summer, I said, hey, presenter who has been teaching calculus for 30 years and talks to college professors and whatever, why can my students not do this? Or is that acceptable? Do you know? And she said, no, that's wrong, but I don't know why. It's just wrong. So I don't know what to tell you guys, but don't do that. So you need to set up one for each thing separately. So instead of writing one limit, let's split this one up. First, do check for any discontinuities. I don't have any because e to the 2x is never going to be negative 1. So I'm going to turn this into negative infinity. Let's go ahead and write our limits too. Limit as a approaches negative infinity from a to 0, e to the x over 1 plus e to 2x, plus the limit as b approaches infinity from 0 to b of the same inside. I'm going to copy it. Duplicate. Right. So now what that allows me to do, notice it's split up at 0 such that the sum of these integrals is still the same as the original, but I am fine with the 2 zeros. There's no issue there. And really the only reason I chose to pick 0, it could have been 1 and 1. That's fine. It could have been 2 and 2. That's fine. It could have been 15 and 15. That's fine too. Makes no difference really. But the reason I chose 0 is usually 0 is kind of nice with our, like when we have to insert those numbers. We have to make that substitution. All right, so now the trick about these things is if one of these is infinity in the end, the whole thing is divergent. So it really makes no difference which one you do. You can pick one and do one of them. You don't have to do both of them. If we come out with just some number on the first one, then we need to check the second one for sure. But if we get infinity of any kind, then I'm done. I don't have to actually do it. So let's just start with the first one. So limit as a approaches negative infinity of, let's see, if I think about u substitution, if I let u be e to the x, then du is e to the x dx. So that'd be 1 over 1 plus u squared, which is arctangent of u. So this is arctan of e to the x from a to 0. So if I put in my bounds, arctan of e to the 0 is 1 minus arctan of e to the negative infinity. Right, so arctangent of 1, that's pi over 4. Arctangent of e to the negative infinity, this might as well be 1 over e to the infinity, which would be 0, and arctangent of 0 is 0. So this first part equals pi over 4. Dang! So what that means is I have to do the second part over there. So I'm going to move this over a little bit and say plus, at least I know the antiderivative as b approaches infinity of arctan e to the x from 0 to b. And then if I throw in my b, let's see, arctangent of e to the b, what is that? Act. E to the b minus arctangent of 0 is 0. Oh no, arctangent of e to the 0, right? So same idea as this. It'll come out the same since it's e to the 0. So this will be minus pi over 4. Okay, so if I evaluate my arctangent of e to the infinity, that'll be tangent as it goes to infinity, arctangent as it goes to infinity, which is pi over 2. And then I have that minus pi over 4. So this whole thing comes out as pi over 2. Gotta know your unit circle stuff. Remember, while it will be okay, I don't like it, but it's okay to leave this on a free response. This is how they will have it on the multiple choice every single time. So I need you guys to be good at simplifying. All right, part F here. So this looks all good and dandy, except x cannot be 0. So I need to split this up from negative 1 to 0 plus integral from 0 to 2. And I'm going to rewrite this as limits. So limit as b approaches 0. Now let's think about this graphically. If I am between negative 1 and 0, there's my area for the first part. So I need to approach 0 from the left, from negative 1 to b of x to the negative 3 dx. Right. And then again, just like in the last one, if this one comes out as infinity or this one comes out as infinity, the whole thing is divergent. So let's just work with this left-hand one, this first one that I wrote here, and then we'll see how it comes out. So this will be limit as b approaches 0 from the left. Let's see, x to the negative 2 divided by the new exponent, so negative 1 over 2x squared from negative 1 to b, which negative 1 over 2x squared, but I need to throw in my b's. Minus negative 1 over 2, plus, plus, plus. So this negative 1 over 2b squared will look something like this. And as I approach 0 from the left-hand side, that's going down to negative infinity. So this is negative infinity plus 1/2. So it really doesn't matter what the rest is. Since this comes out as an infinity, this whole thing is divergent. All right, and just to kind of double check with you guys too, on this other one, for like the bounds, I'm just going to set up the limit. It would be limit as a approaches 0, but since I'm going from 0 to 2, I'm getting closer to 0 from the right-hand side. So 0 from the positive side, from a to 2, 1 over x cubed dx. And then you could work it down if you needed to from that point. But since we got divergent on the first half, the whole thing is divergent. All right, I think this might be our last one. Yeah! All right, so the issue here, right, I don't have any infinities in my integrand, but I do have a 1, and x cannot be equal to 1. That's not possible here. So on my interval 2, from -5 to 1, I'm coming in right there. So I'm going to approach 1 from the left-hand side. -5 to b, 1 over x minus 1 squared dx. And if you need to think about the u substitution, you can say let u be x minus 1, then du is dx. So this is really just 1 over u squared. So limit as b approaches 1 from the left. So the antiderivative of 1 over u squared is -1 over u. So this is just -1 over x minus 1 from -5 to b. So limit as b, that's an ugly b, -1 from the left, -1 over b minus 1 minus plus 1 over -5 minus 1. All right, now I need to think about the graph of kind of -1 over b minus 1, so -1 over x minus 1. That will have an asymptote at +1, and normally it would go like this, but since it's negative, it's reflected. So we have a graph something like that, and as I approach 1 from the left, my graph is going up forever. So that first part is going to infinity, and then I would have -1/6, but that infinity overtakes everything and makes this whole thing divergent. Alrighty, hopefully this helps. As always, please let me know what I can do to help you guys out. Here's a monkey for good luck. He's a happy monkey with a banana. His legs getting eaten by his tail. You can also look around your house and look at how sad the power sockets are all the time. They're just like, yo man, why are you stealing all my power and like shoving things and shoving prongs into my face? This is terrible. So sad. So sad. So sad. Okay.